In this mini lecture, we're still in kinematics of a particle, but specifically we're going to be looking at curvilinear motion, and within that, general components as well as rectangular components. So we're going to be able to actually describe the motion of a particle that's traveling along a curved path, and then we'll relate the kinematic quantities in terms of the rectangular components of the vectors. So taking a look further, you see the picture to the left. So this is the picture that shows the path of motion of a plane, right? So the path of motion of a plane actually can be tracked with radar, and it's X, Y, and Z coordinates, right? We're talking relative to a point on Earth. It's X, Y, and Z coordinates recorded as a function of time. So the question we'll answer is, how can we determine the velocity or acceleration of the plane at any instant? And then to the right, a roller coaster, so we see it there, a roller coaster, the car of a roller coaster travels down this fixed helical path at some constant speed. So we'd probably like to know, how can we determine its position or acceleration at any instant, right? And also, if you are designing a track, why is it important for us to be able to predict the acceleration of the roller coaster car? Okay, so general curvilinear motion. General curvilinear motion. So a particle moving along a curved path undergoes this curvilinear motion. So since the motion is often three-dimensional, then we have to say vectors are usually used to describe the motion. So a particle moves along a curve that's defined by the path function s, So the position of the particle at any instant is designated by the vector r is equal to r of t. So both the magnitude and direction of r may vary with time. Both the magnitude and direction of r may vary with time. If the particle moves a distance along the curve during time interval delta t, the displacement is determined by vector subtraction. And what we'll do is delta r is going to be r prime minus r. So again, the displacement is determined by just using vector subtraction. Okay, velocity. So velocity represents the rate of change in the position of a particle. The rate of change in the position of a particle. The average velocity, right? The average velocity of the particle during the time increment delta t for us is just going to be velocity sub average is equal to delta r over delta t. There's instantaneous velocity. The instantaneous velocity is the time derivative of position. The instantaneous velocity is the time derivative of position, dr dt. The velocity vector, v, is always tangent to the path of motion. The velocity's vector is always tangent to the path of motion. So the magnitude of v is called the speed. The magnitude of v is called the speed. Since the arc length delta s approaches the magnitude of delta r as t approaches 0, right? So let's state this a little bit slower. Since the arc length delta s approaches the magnitude of delta r as t approaches 0, the speed can be obtained by just differentiating the path function. V is equal to ds dt. The speed can be obtained by differentiating the path function. V equals ds dt. But just note that this is not a vector. This is not a vector. Okay. Here we look at acceleration. Acceleration. Acceleration represents the rate of change in the velocity of a particle. And acceleration again represents the rate of change in the velocity of a particle. So if a particle's velocity changes from, let's say, v to v prime over a time increment delta t, then the average acceleration during that increment is a sub avg is equal to delta v over delta t, which is equal to v minus v prime over delta t. All right. The instantaneous acceleration, the instantaneous acceleration instantaneous acceleration is the time derivative of velocity. It's the time derivative of velocity. So a equals dv dt. So that's d2r over v squared. So the plot of the locus of points, the plot of the locus of points defined by the arrowhead of the velocity vector is called a hodograph. It's called a hodograph. The acceleration vector is tangent to the hodograph, but not in general tangent to the path function. The acceleration vector is tangent to the hodograph, but not in general tangent to the path function. All right, now we're looking at specifically curvilinear motion and rectangular components. Rectangular components. So it's really convenient to describe the motion of a particle in terms of its x, y, z, or rectangular components, right, relative to a fixed frame of reference. So the position of the particle can be defined at any instant by the position vector. R is equal to xi plus yj plus zk. So again, the position of the particle can be defined at any instant by the position vector. So the x, y, z components may all be functions of time, right? i.e. x is equal to x of t, y equals y of t, and z equals z of t. So we have the magnitude of the position vector. The magnitude of the position vector is r is equal to x squared plus y squared, x squared plus y squared plus z squared raised to the 1/2 power, right? And all that means is to take the square root, right? Um, the direction of r is defined by the unit vector. Is defined by the unit vector. It's u sub r is equal to 1 over r times r. So that quantity times r. So the direction of r is defined by the unit vector. Okay. Look at rectangular components. Rectangular components. Velocity. So the velocity vector is the time derivative of the position vector. The velocity vector is the time derivative of the position vector. We have v is equal to dr dt equals d xi over dt plus dy j. Let's make that a little bit more clear. Yj over dt plus dzk over dt. All right, so since the unit vectors I, j, k are constant, right? So the unit vectors I, j, and k are constant in magnitude and in direction, then this equation, the previous equation, reduces to v equals v sub x I plus v sub y j plus v sub z k, right? And this is where, in stating this, where v sub x is equal to x dot, right, dx dt, v sub y is y dot dy dt, and v sub z we can say is z dot dz dt. Okay, and then the magnitude of the velocity vector, the magnitude of the velocity vector is going to be v is equal to the whole quantity of vx squared plus vy squared plus vz squared. All right, and then I'm going to raise that to the 1/2 power. The direction of v is tangent. The direction of v, as you can see, is tangent to the path of motion. The direction of v is tangent to the path of motion. Okay. All right. Rectangular components. And now, this time, acceleration. Acceleration. So the acceleration vector is the time derivative of the velocity vector, right? The acceleration vector is the time derivative of the velocity vector, the second derivative of the position vector. So A is equal to dv dt d squared r over dt squared, and that's a sub xi plus a sub yj. Oops, sorry about that. It should be j plus a sub zk. All right, where a sub x is equal to v dot sub x is equal to x dot dot equals dv sub x over dt. Um, I'll write this out as well. A sub y is equal to v dot dot sub y is equal to y dot dot is equal to dv y dt, and then a sub z is equal to v dot sub z is equal to z dot dot is equal to dv z dt. Right. Okay. So now we can say that the magnitude of the acceleration vector, the magnitude of the acceleration vector is A is equal to, we can take the square root of ax squared plus ay squared plus a squared. All right, we can take the square root of that. And just in case you haven't noticed, the dot notation, like x dot, y dot, z dot, represent the first time derivatives of x equals x of t, y equals y of t, z equals z of t, respectively, right? Same thing for the two dots, right? The second time derivatives of the functions. Okay, so in moving forward, the direction of A is usually not tangent to the path of the circle. The direction of A is usually not tangent to the path of the circle. I'm sorry, of the particle. One more time. The direction of A is usually not tangent to the path of the particle. All right, let's take a look at our example. So we're given that the box that slides down the slope described by the following equation, y equals 0.05 x squared meters, where x is in meters, right? And then we have the following for v sub x and a sub x. We have v sub x here, and then we have a sub x at x equals 5. All right, so we're told to find the y components of the velocity and the acceleration of the box at x equals 5 meters. So what's our plan? We note that the particle's velocity, right? So the plan is to note that the particle's velocity, that can be found by taking the first time derivative, right? First time derivative. And this is taking the first time derivative of that path's equation. And the acceleration can be found by taking that second time derivative, the second time derivative of the path's equation. So we want to we take a derivative of the position to find the component of the velocity and the acceleration. All right, so our solution. So we find the acceleration component by taking a time derivative of the position. Y is equal to 0.05. Oops, let's clear that up. 0.05 x squared. So we have y dot, remember the dot, is equal to 2. So we're just taking the derivative times 0.05 x, right, x dot is equal to 0.1 x dot. So we find the acceleration component, by taking a time derivative of the velocity, right? Find the acceleration component by taking a time derivative of the velocity, right? Y dot. So we have y dot dot 0.1 x dot plus 0.1 x dot first and second derivatives. So then we go ahead and sub in the x component of the acceleration velocity at x equals 5, right, into the y dot and the y double dot. Okay, so since x dot is equal to v sub x is equal to -3 meters per second, x double dot is equal to a sub x is equal to -1.5 meters per second squared at x equals 5 meters. Then y dot is equal to 0.1 x dot equals 0.1 times 5 times -3 equals 1 negative meters per second. Okay, and then y double dot is equal to 0.1 x dot plus 0.1. Okay, gonna get us 1 negative 3 squared plus 0.1 times 5 negative 1.5. Do that 9 minus 0 meters squared.